So hello everyone. Mr. Ujaval got his master's in Geospatial Information Engineering from the University of Wisconsin-Madison. After joining Google Incorporated in California, he moved to India in 2006. He was one of the early employees at Google India and part of the team that launched Google Maps for India. He worked on multiple geo teams at Google and led the GIS team in India. He was also the lead trainer for Google Earth Engine in India and trained over 1,000 researchers, scientists, and engineers.
Thank you for the introduction. Thanks to everybody for joining here in this workshop. Thanks to all those who are being online. This is a hands-on workshop on land cover change monitoring. This is an important topic. If all of you were there with the keynote, listen to the keynote. Land cover is one of the key elements that you need to monitor changes, to quantify effect and understand what's driving the change in your region. We have the slide here. So Vigna, you can share the link in the chat as well to get this presentation. All you need is this one link, and all the links you need further are in the presentation. So get the presentation, and all the stuff you need will be part of that. We also need an Earth Engine account for this workshop. So we have 30 minutes or so before we need that. So please, if you don't have one, go and get one. The instructions are there in the slide here. This is the agenda. We'll start with a brief introduction of Earth Engine and the data set that we are going to use. It's called Dynamic World. Before we go forward, how many of you have used Earth Engine before? A few here. If you've not used Earth Engine before, this workshop will give you an overview of what is possible, what Earth Engine can do. And then once you learn it, you can implement it. For those who have done Earth Engine, this will also give you some new techniques and skills, and you'll learn about some new data sets that will help you become more productive. We'll start with the lecture, giving you an overview of this data set and what it can do. We have quizzes. I like my workshops to be interactive and fun. So we'll do a quiz. The quiz is open to everybody online, offline, and the people who get the highest score will get prizes. I have prizes just to motivate people. We have this beautiful Earth Engine mug. You have a chance to win this if you pay attention in the class. We have two quizzes, so you have two chances. We also have this nice mouse pads and some other stuff. So again, we'll open up the quiz. It's just for fun and recapping some of the stuff we learned. Then we'll dive into the applications. This is the core of the workshop today. We'll say, how can you build this application to monitor change in land cover? And then we'll do a second quiz based on the new concepts we learned in the workshop. Bit of background on me. I come from a traditional remote sensing background. So today, if some of you see a lot of code and me typing furiously and doing all the stuff, I didn't learn that in college. I grew up in remote sensing using desktop software, and that was my world for a long time. But then I got hired at Google, very early days of Google, and I had to learn programming, automation, and I discovered the power of being able to build your own tools, build your own systems, and that's what I did for a long time. I used to also teach about that part of the Earth Engine team at Google, and also taught a lot of people. I left Google 3 years back, and since then I've been running my own academy about my company. It's called Spatial Thoughts. It's an online learning platform where we try to publish all our course material openly and freely, so you can learn. Several of you may have already accessed that and learned that. We focus on QGIS, Earth Engine, Python, and GDAL. So these are the 4 core technologies. We have all levels of materials there. It's used by more than 1 million people everywhere. And everything we do, including this workshop, will be open source and free. So feel free to leverage those materials and use this. We also teach the same material in online and offline workshops like this. Most of the work I do is online. So we have online cohort-based classes. Every month there's a new class. People come in from all over the world and we learn together, and I teach in a live class. So, and we are also close partners of QGIS. We are the only QGIS certified training provider in India, and we are very closely associated with the QGIS project. We have TAs. I'm glad to have Santosh here in the audience. He worked with me before, so great to have him teaching a workshop with you again. Santosh, you can introduce yourself. And we have Vigna supporting people online. Vigna works with me currently. Both Santosh and Vigna are both experts in Earth Engine, so they'll be happy to provide support. Vigna, you can introduce yourself.
So, I work as training associate with Special Thoughts, and for this workshop also I'm providing training, like I'm supporting participants who have joined online. So you can just post your queries in chat, and I'll come up with the solution or provide you with some links. And yeah, all the best for the workshop. Thank you.
Thanks, Vigna. So since many people are new to Earth Engine, I want to spend just a few minutes telling you what Google Earth Engine is. Google Earth Engine is a remote sensing software that runs in the cloud. When it came out almost 10 years ago now, it was a very, very different system. It was a revolutionary system. It still is in a lot of ways. When you do any data processing of climate data, remote sensing data, you want your data on your computer and you're working with the data on your computer. And that is limiting because all the remote sensing data are very large. You need to do large processing. Still, most of the software that we use do not leverage all the compute power that they have, even on your own machine. So you can't leverage that. So Earth Engine changed all of that. It provides you a lot of data. You never have to download any data again. Earth Engine takes the data from the different data providers. It includes all public domain data sources, Landsat, Sentinel, MODIS, all of that. It has the pipeline where as soon as a new scene is available, it'll fetch it and put it in Earth Engine. So now you never have to download it again. You just have to say, I want this scenes or I want all the scenes for this date range, and you get it. Also, a lot of the remote sensing data comes in formats which are not very easy to work with. NetCDF, HDF, people who have struggled with this. Earth Engine team does all of the hard work of converting that into format which you can use. You can correlate different data. You don't need to worry about projections or data type, etc. It's all the same data set. And this is a continuously uploading catalog of all the different data sets that's available. Now, if I give you all this data, and this consists about 70 or 80 petabytes of data. When I joined Google, I didn't even know what a petabyte was. A petabyte is 1,000 terabyte. And so it's a very large data. If I give you this data and said, do something with it, you said, I don't know, what can I do with it? I have this laptop, which can handle only a few gigabytes of data. So to do this, Google also gives you computation. It has put, close to 100,000 machines, which you can use as an Earth Engine user. And you can say, all this compute is available, go and use that. You can run your computation on our cloud. Now, you can say, okay, give me computers, but how do I run this? I'm a remote sensing person. I need to create an NDVI, or I need to extract this time series. I don't know how to write code that can leverage this 100,000 machines. Right? So Google also provides you with an API. API stands for Application Programming Interface, which says, we'll give you functions which you can use. And when you use those functions, all the computation you describe, we will be using our data and our compute efficiently in a parallel network. So we don't need to manage, you don't need to worry about how many computers it use, how will it manage, what if this one computer, it didn't process it fast enough. All of this is managed by that. So you just need to learn the API, and that's going to be the focus where you can learn how to do things in Earth Engine for what you want to do. Now you say, how do I use this API? I need to write some code. And in what language do I write the code? So Earth Engine also provides you with a way to write code, save your code, manage your code, etc. And when you write code, you need a way to see your errors, to share scripts and so on. So Earth Engine provides you something called an IDE. It's an integrated development environment where you can do all of that. And this is based in JavaScript. There's also an environment available for Python and R. So whichever language you're comfortable, you can use Earth Engine. A lot of times people get stuck up on this, that, oh, I don't want to learn JavaScript, or I want to use this in Python. You can use all of this. The API is the same in any language you use. So focus your learning efforts in learning the API. Once you learn the API, you can auto-convert between all these languages. There are packages available, and you can use whatever languages. So what can you do in Earth Engine? You can do your image processing task. Earth Engine supports all grid-based data formats. So if your data is projection, real-world Earth projected data in a grid format, you can apply all your image processing tasks. Earth Engine also supports vector processing. This is less known because in the early days of Earth Engine, it didn't support it, but now it's a very capable GIS in the cloud. So you can upload a very large data set millions of points, polygons, and do buffer, intersect, and all of that works efficiently in parallel. You can do terrain processing. You can upload a DEM, do slope, hill shade, etc. Time series. You can take a remote sensing time series and extract data, do processing, etc. Object-based analysis. If you want to extract objects, do change detection, all of that. Machine learning. Earth Engine has built-in algorithms for all the classical machine learning things, linear regression, random forest, and unsupervised, supervised learning, etc. And those are built-in integrated. Earth Engine is kind of custom designed for this task. So if you ever need to do any of this machine learning task, Earth Engine will be super efficient because it's kind of designed and integrated, very closely integrated with all that. You can also do deep learning, but Google has another product for deep learning, which is TensorFlow. So Earth Engine is integrated with the TensorFlow, but it's a loose integration. So in the Earth Engine environment, you cannot run your TensorFlow model. You can go to TensorFlow, build your model, but you can connect to Earth Engine and do all your deep learning tasks. Feel free to raise your hands or type your questions in the chat anytime. So don't hold your questions because it's easier to just ask the question. More important than what you can do in Earth Engine, it's important to know what you cannot do in Earth Engine. Right? Because Earth Engine is a very vast system. So is it worth learning for you? Well, it's not worth for you, but it may not be worth for you if you do any of these. If your work involves creating pretty maps with north arrows and scale bars and all of that, Earth Engine cannot do that. Earth Engine allows you to export your data, whatever analysis you've done, you can download it as shapefiles or GeoTIFF files, and you can then create a map in ArcGIS or QGIS or software. People have hacked together solutions to do this in Earth Engine, but my advice, don't do this. Don't waste your time doing this in Earth Engine. Export your data, and create your maps somewhere else, because it's not designed for it. If you are doing 3D visualizations, you want to do a fly-through, Earth Engine is a 2D system. It doesn't do any 3D analysis. One big limitation is Earth Engine cannot do all the simulations. So if you've ever done hydrological simulations, Earth Engine is not designed for that. The main reason for doing this is Earth Engine is inherently parallel computing system. Every operation has to be able to divide into different parts, and each machine has to process them independently. That's the kind of core computational model for Earth Engine. If you're doing hydrological simulation, to compute the value at 1 pixel, you need to compute value at all pixels. And then only you know what's happening here, right? And that you cannot parallelize that. So it's just the way system is designed, it doesn't lend itself very well to doing this kind of analysis. So to overcome this, a lot of hydrologists use Earth Engine. They do this outside of Earth Engine, import the results, and then you can analyze it. You can do that. Or you can export the data you need for those simulations out from Earth Engine, rainfall, precipitation, temperature, watershed, all of this you can download it from Earth Engine, you can run a simulation. Photogrammetry, you cannot do. If you have raw drone imagery, raw aerial imagery, you cannot stitch them or rectify them, all that. Yes. Yeah. So the question is, if I have processed drone data, also rectified GeoTIFF file, yes, you can use this in Earth Engine. You can upload this data, bring it into Earth Engine. Yeah, you can. If you're GeoTIFF raster, you can upload this and you can use this. And again, a lot of drone providers use Earth Engine because you can now leverage the parallel computing capability to process your data further. Right. Yeah, and you can bring in your data. So Earth Engine, one nice thing about Earth Engine is it's completely open system. You can bring in any data and you can export any data at any point in time. So you say, I'm done with this. Earth Engine cannot do it, or maybe I don't know yet how to do this, but I know, so I can export my data, do something else. Yes, so I didn't put my slide. So I talk about these two Google products. There's a Google Earth, which everybody has used. It's a 3D globe that you can browse high resolution imaging, and then it's Google Earth Engine. The only similarity between those two products is the name, Google Earth. There's nothing else similar. Right? Google Earth is a consumer product for everybody to view the world in 3D. Earth Engine is a professional product for analysts, researchers, scientists to use and analyze public domain. Right? So completely different thing. The name comes from the fact that the same team built both the products. So they just named Google Earth and Google Earth, but very different product. LiDAR processing you cannot do, but once you have processed DEM from LiDAR, you can upload that. SAR interferometry, big topic. Earth Engine made life of a lot of people who do SAR work with Starter very easy because now you can use Sentinel-1 data in Earth Engine, but you cannot do interference. So that's a limitation. Yeah. Yeah, so the question is, can we do land cover prediction? So there are two techniques for primarily doing this. One is a regression technique, where you build a regression model based on historic data, and then you can predict that. So Earth Engine supports both random forest regression as well as linear regression. You can build that. You can also do the Markov chain model, where you can do a pixel-based simulation, and that's also possible. Some of the functions that you need to use for doing this kernel-based operations, I'm going to teach you today. So you can do it. So it's possible to do this kind of simulation. But again, people who are listening online here, land cover prediction requires very accurate historic data. If you just try to do it, you say, so let's say what drives land cover, right? It's, say you construct a new road that drives a land cover. So you need to know, if you're getting data for last 30 years, you need to know for every year, what was the road network like? Right? For every variable, you need 30 years of data to build that model. So you need to create this somewhere, right? You need to know what was the road network of Bangalore 30 years back. That data is very hard to get, right? So to do an accurate land cover prediction, you need historic data, which is hard. So again, it's possible, but be careful about getting very accurate historic data. We're going to use this data set called Dynamic World. Dynamic World is a land cover data. Now, raise your hands if you use land cover data before, any land cover data. What data have you used before? Bhuvan, LUSM, anybody else use other land cover maps? CCI. Right, so land cover is one of the most fundamental products in remote sensing. Almost every analysis will need a land cover product, but they're very hard to get. Most countries do not have openly accessible national land cover product. So you say, I want to know the land cover of Bangalore today, 5 years ago, you don't have the product. There are some global products that are recently available, ESA World Cover, etc. Most of them are yearly frequency. You wait, once a year is over, you wait for a year, maybe you'll get a global land cover product. But what if you need to know what was the land cover like last week? Well, you say, okay, you can build your own model, get the training data, train a model to classify. So supervised classification is widely used in remote sensing. Most of the people who done remote sensing would have done that. And so challenging process, you need ground data, you need to know how to do modeling. If you're using approaches like neural network, you do have a lot of training data. It's very complex. So Google said, can we help solve the problem, make it a little better? So this is the product that was launched a couple of years back, where they take the Sentinel-2 dataset and they do build a land cover model on Sentinel-2 dataset. It's a neural network that they train using large amounts of training data. It's a global model neural network where it can predict land cover at every pixel, and it is available in 9 land cover classes. So every pixel is classified into 9 land cover classes, and it is available for every Sentinel-2 scene since 2015. Okay. Sentinel-2 scene is available every 5 days. So now this model is run on every scene. It's also run on real time. So when a new Sentinel-2 scene is available, they run the model, and within a few hours, you have a land cover model. So now every 5 days, since 2015, you have a global land cover product. Right? The key differentiator here is that here, instead of just getting one value, most of the land cover products will say, this is water, this is forest, this is crop. Right? Earth Engine, also the dynamic world, also gives you the model output, where the neural network ran and say it gave this probabilities of every class. Right? So you have the raw data that came out of the model, and you can take these probabilities and you can refine it further and say the model said this is 30% crop, 50% forest. But in your area, maybe the model got it wrong because it's a global model. So you can get some little bit of training data for your region, refine it because you have those probabilities with you. Right? So you can refine and build a land cover product. Yes. No, it can kind of get you to what the mixed pixel is very different problem, where a single pixel have multiple land covers. How do you do this? So this can give you, if there are two pixels, which have, one is a pure pixel and as a mixed pixel, it'll give you different probabilities, but it is not designed specifically for that. And again, Sentinel-2 pixel is small enough that you don't really have this problem of mixed pixels as much. Yeah, can we use the dynamic world trained model with our data? So it is trained on Sentinel-2 data. So if you want to download the Sentinel-2 scene, the TensorFlow model is open and open source. You can run it locally. If you just search for dynamic world, you'll get a GitHub repository with the code saying that this is one Sentinel-2 scene, predict locally, and you can run that, use that locally. Accuracy assessment, the global accuracy assessment is in the range of 70 to 75%, depending on how you look at it. Again, the dynamic world paper is a published peer-reviewed paper, which talks about how they did this. There's also a new effort that is doing accuracy assessment, not at an annual basis, but a more monthly basis. So again, you can do this. But again, the idea is do not rely on the global predictions. You can kind of refine this for your own local needs. And that's a key idea of dynamic world. Again, the key differentiator, when I first heard of this data, I was like, oh, new land cover problem. I didn't really pay attention to the word dynamic. Dynamic means it's running in real time, right? As soon as a new scene is available, it's classified. And every Sentinel-2 scene is classified. So you want to know what was the land cover yesterday? If there was a Sentinel-2 scene, you'll know. Right? These are the 9 classes that dynamic world produces, all commonly used classes. So if you're kind of trying to monitor the land cover in any of these classes, you can do this. Another key thing is, since you have the probabilities of all these classes, you can say, I will train a model to give a new class. Maybe I'm interested in monitoring mangroves. There's no mangrove class here. But I can take these probabilities, build a simple random forest model to have a mangrove class. Right? Now you can say, I have a neural network plus my random forest doing the work for me. You don't have to do the work to build and run this neural network. It's already done, right? So you can get benefit of all the kind of deep learning effort. With a little bit of more effort, you can refine it for your own class if you don't see your class here. Dynamic world is a very large data set. Yes. Yeah, the good question. The question is, if there's a mistake that we find, is there a feedback loop? Currently, there's no feedback loop. This good idea. A lot of people have suggested Google. Right now, there's no formal mechanism to do this. Again, there are a lot of people, you see social media, just search for dynamic world. People say it gets this wrong, gets this right. But again, the problem there arises is when you say, whatever dynamic world predicted as the highest probability, I'll use that as my class. The solution to that is, obviously, the model is not going to get your local land cover 100% accurate. It's a global model, right? The crops in India look very different from crops in Europe. But you have the model's output probabilities. You can retrain it to detect crops better in your region if you have local training. And that model will be much better than what you can do it yourself, because you have a neural network that is already done the work and you have the input to that. Yeah, so it's a single model that is run on all scenes when it become available. So it's a model that's trained to detect this 9 land cover classes from any Sentinel-2 image. So it's just saying, new scene, I'll predict. It doesn't know what happened before, what will happen in the past. Yeah, so right now it doesn't include any temporal history of that pixel. I think it's, again, a good idea. A lot of people talking about kind of improving this kind of model that has the temporal history of the pixel to kind of make the model prediction, but currently doesn't do that. Each scene is independently run. Yeah, cloud, you won't get any help for cloud cover because this is based on Sentinel-2. So Sentinel-2 is cloud. There's no observation stuff, so you need to use it. So yeah, deep learning is not magic. You cannot see through clouds, but yeah. So again, very large data set. Since you have probabilities of each pixel, petabytes of data, all of this available in Earth Engine. This is what you need to really focus on. You load dynamic world data set, you go to any pixel, query it. This is what you'll see. Look at this region. This is University of Wisconsin, where I did my master's. This is where I used to go and cycle around here. This landscape, how would you classify this? Well, depends on the person, because this landscape is completely frozen in ice at this time of the year. If you go in March, April, when the snow starts melting, it is grassland. Go in fall season, it's all colored forest, right? So it keeps changing all the time. So how do you determine dynamic this land cover? So you get one image of Sentinel-2, and let's say in this image you ask dynamic world, what was the probability? It'll give you this, right? It says right now dynamic within there's a high probability that this pixel is trees, is forest. And these are the different probabilities of this. As the new scene comes in, the landscape has changed, this probabilities will change. How will it change? It will change like this, right? So this is the same pixel throughout the year. You can see there are individual observations. This is one scene, second scene, third scene, fourth scene, and so on. And you can see in the winter, it's all snow. When snow starts melting, the shrubs and the grass start growing. So here is where you ask, it's like, oh, some part of it is shrub, some is trees. Then it becomes forest, stays forest. Forest starts losing leaves, and goes, right? So this is the kind of cycle it says. You have all of this information with you, and you can use this to do your monitoring. Single pixel. Yeah. And now you have this land cover history for all pixels in the whole world since 2015 up to current. So you can kind of get this history, use this to monitor changes. So now if you want to monitor changes, you can say, I want to know which lakes get frozen in this area. Well, you say, give me all the pixels which were frozen in January, not frozen in April. Right? Or high probability of frozen in January and high probability of water in May. And suddenly you found all the lakes that froze globally with just one line of code. Right? You didn't have to build your own model. So this is the advantage of having those probabilities. Biggest takeaway from today, dynamic world is not a ready-to-use land cover product. Don't take this. And there is one band in dynamic world called label, which is the class with the highest probabilities. A lot of people take this, create a map and say, this is my land cover map of land cover. No, don't do this. Because that's output of a global model. You need to apply your local knowledge to refine it, to make it a locally relevant product. So how do you think of dynamic world? Well, don't think of it as a land cover product. Think of it as a product that gives you 9 bands of Sentinel-2, which are focused on land cover. So I get 13 bands of Sentinel-2. I get 9 new bands from dynamic world, which is tuned to detect land cover. And I can use this and create my land cover. I can build my change detection model using this. Instead of going to Sentinel-2 and say, I will figure out how to figure out the change detection. I'll do some index, I'll do the differential. Instead of doing that, just use the probabilities directly, because the model has already done all the classification. And they'll give you much better, cleaner result with less sign of it. So it makes making change products, land cover products, much, much easier. Order of magnitude easier. And that's the idea, that you can do this more frequently. It's more accessible to do this. You can make, if you have working for a company and you have a client and says, I want to monitor this. Can you build an app for me? You can get them in 1 hour. And it's done. Anywhere in the world, you have your change monitoring app. Right? If they want more accurately, you can say, give me some training data, I'll refine this, and I have a better land cover. So, slide, photo from today morning, keynote. The question was, okay, first step in any remote sensing project is land cover. I want to monitor land cover. What is changing? Right? This is what I'm going to teach you today. Right? The second part is important. When you are doing this, change, what you see in the change, you see the change in pixel. You do not know why. So as an analyst, keep in mind always why you're doing this. What is the driver of this change? That's an important thing to understand. A lot of time when we are remote sensing analysts, we forget that. Say, okay, I've created this amazing map. This is changed, but you don't understand the driving factor. So just keep this in mind. I thought it was a good kind of point to keep in mind. But the first step, how to monitor the land cover change, this is what we're going to learn today. 3 examples we're going to do today. Hands-on, everybody can do this. You can now monitor any reservoir weekly or monthly in the whole world. You can create, you're going to select your area wherever you want in the whole world, any lake, any water body. You're going to extract shape files of the surface water boundary every month. Okay? And you can do this, just few lines of code, and you'll be able to do this. So you can do this anywhere in the world. This is showing the KRS dam near Mysore, and see the water level. Summer it shrinks, once the monsoon happens, it will build that. Second one we're going to do is urban change. We're going to build an application of urban growth. So how an urban area changes. So you're going to go and select a city or an urban region of your choice, run the code, and it's going to detect what pixels are getting built up. And again, you need to define what you consider built up in your region. So you will adjust the probabilities, what makes sense for you. This is showing the change in Bangalore. And again, if you ever try to do this, again, doing this kind of work, let's say 7-8 years of change, you need to kind of train a model, it will be very noisy. Here, if you see all of this are correct detections. You'll see all the new buildings getting constructed, all the new layouts being proposed year to year or month to month or even week to week. That happens. You can do this with a week. This is probably just 20 lines of code. Right? I can do this anyway. We'll do this. Then we'll do disaster change mapping, where say something happened, I want to know where it happened, what areas got affected. Landslides happened, deforestation happened, forest fire happened. So you'll get before image, after image, get the probability, compare them, and you can find the area. So this is a landslide near Kurg that happened a few years ago. You can map all the pixels that were not bare before, but now bare. And again, using a simple chain division. So the thing is, you can do it at high frequency. You can do this weekly basis, monthly basis, whatever temporal frequency you like. 3 kind of classes. If you have one of the 9 classes, I want to monitor, flooded vegetation or crops every week. You can do that very easily. There's a continuous monitoring of this. You can do change monitoring. If you want interesting change between any of those 9 classes. What was water before, land now. You can do all the changes between them. You can also do that. And you can do this continuously. You can also do disaster change monitoring. As something happened, you want to know before and after, you can compare them. And again, if you don't have a class that you're interested in mapping or monitoring, you can, with a little bit of training data, you can refine it and use it. I've linked this article where I show the code and the whole process of how to do that. Right? We're not going to do this today. We're going to do these 3 applications. Okay, limitations. Very important to understand. I always focus on what you cannot do. That's the main thing to do, rather than what you cannot do. Right? As I mentioned, the dynamic world is not magic. It's based on Sentinel-2. It cannot look through clouds. SAR data can. Sentinel-1 can look at it. Sentinel-2 cannot look at it. So if you have clouds, you start it. So the example I showed of the surface water monitoring, if I look at the images from September, no land cover there. Why? All images in September were cloudy then. So you don't have observations, you don't have land cover. So that's just a limitation. One further limitation is since Google decided that to make the best use of the computational resources that they will run dynamic world model, not on all scenes, but all scenes which are less than 35% overall cloud cover. If you have a scene that is 70% cloud, say I have still this 30% pixels which are cloud free, you will not have dynamic world. Okay? So regions that are perpetually cloudy, you'll have, you can't do more frequent one. That's just a limitation. They're trying to address this. They want to kind of have a better cloud mask. They launch a new cloud mask this year, the Geo for Good conference. So hopefully they'll apply that. They'll actually give you back all those pixels that are missed. But right now, cannot do that. The third one is kind of major one, is the dynamic world is based on a CNN, convolutional neural network. If you ever run a neural network, convolutional neural network is based on image scenes, image chips, right? Dynamic world, for predicting what's happening at this pixel, it is looking at 10 pixels around, right? So it's a 10-meter land cover product, but for classifying this 10-meter pixel, it's not doing a pixel to pixel classification. It's looking at this pixel in relation to the surrounding pixels and making a decision what this pixel is. That results in a much smoother output. So if you do a supervised classification, you have this salt, pepper noise, right? Dynamic world is very smooth. It's very homogeneous. Right? So you don't have to post-process the data as much because of this spatial context. It also helps on things like urban. This is the only product I know that can classify urban regions. Every product can do built-up regions. Right? You can classify built-up regions. Say this is concrete, this is asphalt, I can classify that. But what's the notion of an urban area? Well, if let's say you have proposing a new layout and you're just digging up roads, it's now urban, right? Dynamic world will pick it up. And there are examples I'll show you where you just start building dirt roads, you classify the whole thing as urban because it's got the spatial context, what an urban region looks like, because CNNs are very visual. But that also means that, other model will classify that as a bare land. Dynamic will say this is urban, right? Also, because of the spatial context, it tends to miss finer details. So if you're trying to detect a pixel or a feature which is just 10 meters wide, dynamic will miss that sometimes. Right? So again, it's smooth, it helps you in some way, but again, limitation, sometimes you miss the finest. That's just the fact how CNNs work. Okay, there are some questions online. Let me address that. All right, any other questions before we move on to the quiz? All right, everybody has the presentation. Go to the slide with the quiz. Even folks online, we'll do a quick quiz. I'm going to open it up. It's closed now, so just wait for a second. All right, quiz is open. Go to the quiz. 5 questions, 2 points each. Go and answer them. We'll give you 5 minutes to answer these questions. Once you answer the questions, submit it. The first few responses with the highest score will get a prize. Even online, if you are in India, I'm happy to ship you your prize if you win this. So please try and attempt this quiz. We'll have 5 minutes. This is on slide 25 of the slide deck. So if you want to get the slide deck is here. This is the link to the slide deck. bit.ly, https://bit.ly/InGARSS Tutorial. And go to slide 25 and you can answer. You can also answer on mobile. So you can take a picture of the QR code and go to slide 25, get the link for that. Code, yeah. So the way it's integrated is you can take your data from Earth Engine, export it as TF record. So instead of exporting as a GeoTIFF file or a shape file, you can export it as a format called TF records, which will give you this image chips directly. So you have, say, I have the city of Bangalore images. I want to export this for deep learning. You need this 256 by 256 images that are used this thing. So you can export these chips directly out of Earth Engine in a format that is optimized for deep learning. So you look at the user guide for TF record export, there are a lot of examples. And then you take those TF records and you say, now I will build a model in TensorFlow. You can use Google's AI platform, which is called Vertex AI now, which is a paid platform in Google Cloud. You can take those image chips and use it in the cloud, or you can build a local model in Colab or Jupyter Notebook, use those image chips, build a model, and you want to predict. You can export your predict image also as image chips, predict it, and you can import it back into Authentic. And so this whole flow is very easy to do if you use Vertex AI, because there are functions you can just export and import directly, and it's live, like we get it live with this thing. But if you use Colab, you have to upload and download manually. That's why it's a kind of loose integration. And there are examples in the user guide that is there. I also have some examples. I will link it on the last slide of this presentation. Right? So I'll link to a deep learning slide. So Vigna, if you can add a slide at the end of the class and link to our Python API presentation where we have the deep learning slide and where I have scripts and Jupyter Notebook that show the whole workflow. Right? So you can review that. So think of this as you're trying to detect mangroves from raw imagery. You have 13 bands, you classify them into mangroves versus non-mangroves. Here you take these 9 classes, classify them into mangroves versus non-mangroves. If you want mangroves, water, agriculture, and this thing, you say, I will take this 9 bands, refine it to 4 bands, 4 classes. So no, the input ones are just your covariates to your model. So your input are these 9 values, outcomes, well, what class it is. So if you have a 3-class model, it'll output 1, 2, 3. If you just have 2 classes, it'll be 0 or 1. Right? So it's a classification based on this 9 probabilities that goes in. So it's a regular supervised classification, but instead of using your Sentinel-2 bands, you're using this probability bands as it. No, that are used for learning, because that's what the model used to say, or you say this point is mangrove. Well, there is a high probability of flooded vegetation, low probability of crop. I'll use that to train a model. And when I have an unknown pixel, I'll use those probabilities to tell you whether it's mangrove or not. Right, so you can have your training data. You can train a model, a random forest model. If I say this is high-rise building, low-rise building, and drop those training points and use those 9 bands as input, build the model, which will classify those into low-rise versus high-rise. So it's a supervised classification. So you know, when you use the model, you predict your TF records. You can import those TF records into Earth Engine. The Vertex platform. There's a function in Earth Engine called predict from AI platform. So I say my model is in AI platform, predict directly into Earth Engine. So, but that's a paid model, so paid service, expensive paid service. So be careful when you use Vertex AI, because Google makes a lot of money through the deep learning thing, but you can do it for free in the workflow that I've linked in the last slide. Yeah, you can take the TF records, parse it, and convert it. The question is about texture, and does it? Yes, it looks into the spatial distribution. Yeah, CNNs are very good for that. So you don't need to kind of do the texturing yourself. This is much more advanced level. It has much better spatial context than a regular model. Yes, similar. CNNs are identifying those objects and from the images. Yeah, when they built it, this was cutting edge. In last 1 year, this is not cutting edge anymore. So yes, I'm sure somebody at Google is working on a transform model for this. Yeah, I was talking to somebody, and this is still cutting edge for us, right? Like remote sensing. I was talking to somebody like, why are you using such an old school model? It was not old school last year. So last year has been crazy for AI. So, all right, the quiz is done. I'm going to close this, and let's just go through the questions. All right. Dynamic world is derived from which data set? Sentinel-2, which is one of the classes not covered here, Savannah. Right? But if you want Savannah classes, you can add your training data, refine. What do this represent? Probabilities, right? So they are not reflective values. This one is a tricky one. I think many people go with it. 2050 onwards. So dynamic world is derived on level 1 Sentinel-2 data, not level 2 data. SR data, which is much more better, because level 2 data starts from 2017. They wanted a larger time series. So it's based on Sentinel-1 level 1. Again, you can do all of this. So hope you checked all of this. Yeah. Yeah. Yeah, so that's what the example of landslide, right? So landslide example I showed you, that's using dynamic world. Not download, you can find it in Earth Engine itself. Yeah, so there's an article that's linked there, which has an Earth Engine script to refine if you want to do. How you do supervised classification in Earth Engine? Have you done any supervised classification? Yeah, so once you learn, there are a lot of guides. It's the same simple drop points in Earth Engine, and you can just do this. It's a 10-minute process if you know what you're doing, and you can refine it. Right? So it's a simple one. All right, let's look at the prizes. Right, we have two people who did very, very fast. So we have Abhinav Upadhyay. Abhinav is here or online? Okay, I think Abhinav is online. Congratulations, Abhinav. We're going to send you your prize. Let's see. Anjali? Yes, congratulations, Anjali. Here's your Earth Engine mug. We'll see one more. Yes, so for 10. Okay. Shiva. Shiva is here
Yes, sir.
or
Yes, I'm
online. So
yes, sir.
Shiva, congratulations. We'll send you one prize.
Thank you, sir. Thank you. Yes, sir.
Suresh Kumar? Yes, so this one. Congratulations. Right, folks, Vigna will be in touch with you who won your prizes online and will ship your stuff. I typically cannot do this because most of my participants are outside in India, but since you're in India, I'm happy to send you one. So, congratulations. All right, some fun. People who didn't get the prize, I'm not taking anything back. I'm going empty-handed. So I have still 5 prizes to give away. So stay tuned for quiz 2, and you can win that. All right, so let's start the hands-on part. We're close to lunch, but I want to still get through the first part. Please, if you just joined in, please get this link, scan the QR code, or just get the link on a laptop. If you want to do hands-on part, it's more fun hands-on because you can see your own region. Right? I'll show you something, it look cool, but if you go to a region that you're familiar with and see the changes, and that's the beauty of this global model, right? It's the global model that can detect changes anywhere. So online also, please follow along, try to do this. First case study, monitoring surface water. This is what we're going to do. Select any region of the world, and we're going to see how the surface water changes from month to month. So whatever time period we choose, remember we have different probabilities of each image. So let's say you want to do month-to-month monitoring. Each month might have up to 5 Sentinel-2 images. That means we have up to 5 probability observations. So I said this pixel was observed 5 times this month, and these were the probabilities. So the first step we'll do is, if you want to do month to month, let's just average out the probability. You can do a composite. Let's say every pixel will get the mean probability. You can do max, you can do median, whatever is appropriate, and you can do this. Get the probabilities for with the each region time period that you are considering. Then we'll say we have this 9 class probabilities. There's one class called water, but again, it's a probability, it's a continuous raster, right? So you need to say what threshold you define to extract water. And you can say, I will say anything that's more than 0.5 probability is water. And see how the results are. You know, sometimes in Indian lakes, we have a lot of sediments, a lot of vegetation. And, you know, a pure natural lake in the Alps might be clearly classified as water versus something in India may not be. So you say, okay, I have all the information. I can say water here is maybe something which has got, you know, maybe greater than 0.4 or 0.3 probability of water and some probability of being flooded vegetation. There's, you know, flooded vegetation around, there's floating vegetation on top. So I'll use both of this to figure out what I would classify as water. Again, that's as an analyst, you make that decision, what makes sense for you for monitoring that. You can be done then. You can just say, I will export this data, done. But I want to show you some advanced techniques, especially some morphological techniques that will help you not only for this, for other things. We'll say, we'll apply some filters to say, since I want the whole water body, when you detect it, maybe there are holes in the water body, or there are certain pixels which are outside, which is, you know, kind of surrounded. So we'll say, let's just smooth everything, fill holes in the data. We'll also remove isolated pixels around the water body. I have a clean outline of the water body. We'll convert into vector as a shapefile and export this. So the idea would be that you have this script, you run it, you get a shapefile of the surface water area for whatever region. An Earth Engine can scale to arbitrary large regions. You can run it on entire India, you get surface water map of entire India every 5 days. Right? So we'll do this and learn how to do this. So we'll start. Everybody can come to this slide. Go to the script 1.1 here. Click on this link and open the script. This will open the Google Earth Engine code editor. If you've signed up for an Earth Engine account, you should see something load on your screen. If you are asked to sign in, you have to sign up for Earth Engine account. Earth Engine doesn't like you sign into multiple accounts. You might say, I have an Earth Engine account, but if you have 2 Gmail accounts in the same browser, make sure to sign out of all and sign in only into one account that you're associated with Earth Engine. So open the script 1, we're going to do step at a time. So first we'll do this one. This will spend the longest time. I'll explain the code. We'll see the dynamic world, what it looks like, and then we'll open each of the script. The completed script is here. So you can just, if you are, after we've learned, you can just go and use that anywhere in the world. Say, I don't like JavaScript, I want to do this in Python. I have a notebook. Same code, but just using the Python API using that. Right now, focus on learning what the script is doing and how you can change it for your use case. Okay, so everybody open the script. Please ask for help for here if you have trouble getting to this thing. So I'm going to open the script. Should see this on your screen. An important note for users of Earth Engine in India, there are 2 URLs for Earth Engine. There is a code.earthengine.google.com and .co.in. Indian users, make sure you use co.in. That has the correct international boundaries that we need. So when you produce any data, it will be using the correct boundaries. All right, anybody needs help? Who is trying to follow along, needs help, please let me know. Online, hope everybody is able to follow. Please ask for help. All right, so what we're going to do is, the way we have structured the script is you have this geometry input, which is the polygon that we have drawn anywhere in the world. Let me just run this script and show you what the script is doing. So there's a run button. When I click the run button, you'll be zoomed into this region. This is the KRS dam. What I've done is, first step was that I've defined this polygon. And the way you can do this is there's a drawing tools here. So if you want to change this for your own region, what I want you to do is the first step is once you have the screen, go and delete this geometry. When you hover over this, you'll see this delete button here. Go and delete that. So this is my area of interest, not yours, right? So go and find your area of interest. You can use pan and zoom, or you can just search for this. So let me just delete this. And you can search for any place. I say I want to go to Bangalore. Go to Bangalore and find any water body that you're interested in. You can say I want to monitor this Madivara Lake. There's a polygon tool here. So there's a polygon tool here. Go and draw a polygon for the region that you're interested in. And you should see a new geometry object here. And your analysis will run that. Right? So that's the main change that you want to make for this region. Make sure you delete it first. Don't draw a new polygon. If you draw another polygon, it'll be 2 polygons. It'll run analysis on both. We want only 1 polygon to be drawn. Right? And once you're done, you can run this. If you've done everything correctly, you should see a map of some water from dynamic world in this region. And you can then turn off this geometry to see the map. Right? So this is the water that was detected using dynamic world. So it's the first step. For folks who are online, in this slide also, I show exactly how to delete the geometry and draw a new geometry. You can use that technique. So I'm going to go back to the original script. Let's go through the script. This is using JavaScript as a language, but all the work is happening using the Earth Engine API. So the first step, we're going to define a time period. So we are saying we're going to monitor. The way we have structured the script is we are monitoring monthly. So we say, I want to monitor this year and this month. You can change it to do any month. And again, if you're doing this and say, I want all months of last, say, 7 years at once, well, you can do this. If you know Earth Engine, you can put this in a function, map it, and do this. But right now, let's learn how to do 1 month at a time. So you can change the months to any time. This creates a start and end date. Earth Engine users, make sure you create your dates like this, not with strings. This is much more flexible, and you're saying from this year month, start date is this, end date is advance 1 month. If you see a lot of clouds in that month, you can change it to 2 months. So you'll say, give me the average between 2 months, so you have more observations. And you can adjust for that. Once we've done this, we take the dynamic world data. This is available here. So Google Dynamic World V1, this is the model. This is a data set containing all the images. We filter it for all the images collected between the start date and over the geometry that you have chosen. This gives you all the images, dynamic world images, and the probabilities. These are the 9 bands that we want to get from this data. So we select those bands, and then here is where we compute the mean probability. So you can see we're doing mean here. So say, give me all the bands and all the mean probability. If you want maximum probability of this, sometimes it's helpful, like you want to have a crop thing and we say, give me the maximum crop probability. You can do max there. So it'll give you the max per pixel. This is a per pixel composite. Just to see the data, we are also creating a Sentinel-2 composite, just to see what original Sentinel-2 images look like. And we'll see what dynamic world says. We'll visualize this. So we're visualizing this between 0 and 1. Probability is between 0 and 1. So we are visualizing the water band, because that's what we're interested in. We have a palette of colors, white to blue. And we want to visualize this. So let me run this. And this is your first look at what dynamic world looks like. So at the bottom here, so these are the layers. I'm going to turn off the top layer. So this is what Sentinel-2 sees in this month. So this is the median Sentinel-2 composite of what was observed here. And you can look at it. This is the water. These are the water pixels you can see kind of from the image itself. Right now, your job is to extract what is water, what is non-water. And we say, let's use dynamic world for doing that. So I'm going to turn on the dynamic world probabilities for this. This is what dynamic world thought of this region in this month. I'm going to take this and switch to the inspector tab. On the right hand side, you have the inspector. I'm going to switch to inspector and click somewhere on the map. Click here. And you can see that at this pixel, these were the probabilities that dynamic world predicted of this. Right, I clicked at the middle of this water body. So you can see the water probability is 0.75, 75%. Very confident, the model is confident that this is water. What happens near surrounding areas? So let's go to this region. Don't go by the base map, go by the Sentinel image. So look at the Sentinel image, you can see there is kind of the vegetation here. You see there is, some embankment here, vegetation. It's not, it's kind of, water is merging. It's a water area. Let's see what dynamic world says there. I'm going to click here. And dynamic world says, this is only 13% water, according to dynamic world. It is mostly flooded vegetation. Right? So now if say, do I consider that pixel as part of my water body? That's up to you to decide what's the application. If say I consider that as part of water body, you can say, give me all the pixels which are high water and high flooded vegetation. If you say I only want pure water, I don't want to consider vegetation, then only select the water pixels. Right? So this is what I meant. Don't use dynamic world directly. Refine it for your particular use case. So once you load it, you say this is what dynamic world got this. Now I can define and do this for my region. Okay. So please try this for your region, inspect it and see what the water probability looks like for your chosen reservoir. Anybody needs help here? I can come in and help. Yeah, 0.5 is pretty good because see, the global model is trying to kind of detect water everywhere in the world, right? So even in the most purest water, you'll get like 0.9. So 0.5 is pretty good. So you can then say my threshold will be 0.5. You'll try the threshold or 0.4 and see what it looks like for that. It's just the what the CNN model is doing. It's looking at the image in all these bands, and it's saying, is it water or not? And it's trained to detect water from, say, thousands of images across the world. No, they have done systematic sampling across the world in different land cover. In the dynamic world paper, they have shown what are the sites. You can also download the training data. They did polygon training data. They said this is water, this is vegetation, and those polygons are also available to download. So you can see what the model is. So it's just trying to say, does it look like water? How confident the model is around that. So generally, 0.5 is a good threshold to start, but depending on the region, 0.4 is also good. So you can try this. And again, that's why I want you to try in your region, right? So because this will be dependent on what you're trying to do and your region, what it looks like. So two problems are front. One is it will mostly be cloudy for during the flooding season. So if you have a clear view, what will happen is the street will have before probability of very high urban. Afterwards, it might be still 0.6 urban, but there might be 0.2 water, right? Or something will change because it will look different, right? So you can use that to define a model set. Can we detect that? But all the flooding, since the thing I've tried doing this, most of them have clouds for flood. Yeah, but to classify this, it is looking at the surrounding pixels. And so it will not be classified as water completely. It will say there's something different. It's a different kind of urban now because there's a water somewhere here, right? So it'll be different. Yeah, so you have to figure out what is the change and you can use this threshold to change that. All right, I'm going to move on. I'm going to at least finish the first part before lunch break. I'm going to move to the script 1.2. You can stay in your region script. I'm just going to show you what are the new stuff. Maybe you can open this in a new tab and copy paste the code if you want to. So the next step we want to do is extract water. So here we say, I have these probabilities. Let me extract the water out of this image because I want to export this. So here we define our threshold. 0.5 is a good starting point. And we say water is anywhere where the probability of water is greater than this threshold. So any pixel where the water is 0.5 or more, that's water. And let's look at that. So when you run this, this is a Boolean operator. So it'll give you a 1-0 image. And you can take this and say, display 1 in blue, 0 in white, and you can get the Boolean image. Next one I'm showing you. You can see this region I was showing you, right? There is a low water probability, this is flooded vegetation here, right? There's water here. So now when we define a threshold, you'll see what the output image says. This is water. All the stuff in blue is water. Other is not water because it's more than 0.5 probability. And it's kind of pretty good. One line of code, right? One line of code, you've got water. Challenge you to generate this clean output from any data set or any model, right? Because this is already you're working with an output of a CNN, right? You're not doing this, all the work, hard work that's there. Now you've got this, if you go and check all the pixels, these are all water bodies. And you've got a pretty usable output that you could define. Now, the question was, can we say, I want to now also consider those flooded pixels with vegetation on the embankment. So I want to also consider them a part of the water body. How do we do that? We're going to go this part. Turn off this line. This line just zooms in to the whole region. I'm going to turn this off so I can see this here. So I have some other code here. This is commented out in JavaScript. This 2/, that means it's commented. It's not running right now. But I can uncomment it and I can run this. So I can select this one and control / is a bulk comment or uncomment. So I can just bulk uncomment and say, I have this another criteria that I want to select all pixels which are more than 0.3 of flooded vegetation. And I can combine those two criteria. So this is how you combine two criteria. Water is where the probability of water is greater than water threshold, or probability of flooded vegetation is greater than threshold. So you're selecting the don't do and. You'll probably not find any pixels where both conditions match, right? So or, and let's run this. So if I uncommented this, run this, we can focus on this area. So this is water. In the first part, this was only the water boundary. Now let's run this. Right. So that also got detected as our water. And this is our refined model of water detection for the region that we work. And this will remain kind of, you can use the same model month over month because your local region will be classified using the same model. Try this. If you want to try this, you can either copy paste this code from here onwards into your own script that you're building and run it, or you can just use the part 2 script here and extend. I want to show you what happens. So let me just. So this is my model for January. Let me just change the month. So I want to now detect water in February. I just change this. I run this. New dynamic world images. The new threshold. I got water for February. Great. Right. And when we have the full code, you can just download the shapefile. And now we change the monthly. This was in March. You can see the changes in water month to month. Again, images are every 5 days, so you can even do advanced 5-day. Right? You can just do instead of advanced 1 month, you can say advanced 5-day, and you can do this. What happens in September? This is September, right? So what happens? You have valid observations only here. Because Earth Engine applies, the dynamic world applies a mask to mask clouds and cloud shadows before it is sent to the model. Because cloud shadows are notoriously look similar to like a dark buildings, right? So it doesn't want to misclassify it. So it masks all clouds and cloud shadows. So it removed all the clouds, whatever non-cloudy pixels got classified. Now you say, what do I do? Like you can't do it. Don't use dynamic world for September. Or you can say, I'm looking at September, maybe I can't monitor September, maybe I can monitor September to October and November. So I can advance it by 2 months. So now I'll get all cloud-free observations within the 2 months and give me the model. Now you have enough images and you have a model. Right? So again, you limit it by the cloud. 10, 5 each month. Yeah. So this is a good question. This is a technique called, like we have 10 observations. Which observation we are considering? So in this case, we are doing mean. So we take all cloud-free observations for this 2 months, and this is the mean probability of that. So we are doing mean. As I mentioned, you can do max, min, whatever you makes sense for that. Like you are trying to map the maximum water extent in these 2 months, just do max. That means what was the maximum probability that was observed during these 2 months. It's observing the probabilities of different classes. So depending on your application, mean is a good starting point, but depends on what you want to do. Like you say, I have this 1 month period. I want the maximum water extent within the 1 month. Then you can do max. If you say, I want average water extent. Yeah. Other questions? Raise your hands if you tried it on your own region. How does it look? Does it work? Did you check the probability of this river pixel? What does it look like? Can you inspect the pixel and see what turn off the geometry? See, there's some probability of water there. Yeah, maybe there's a, let's see what it's detecting. It's bad because it's a dry bed, right? Yeah, so you can also say where the water probability, I can see it's like 0.2 or something. So if water probability greater than 0.2 and bare greater than 0.4, and then you'll detect that, right? So you can kind of figure out what is there. Yeah, good question. The question is, whenever we do compositing of Sentinel-2 Landsat, we are doing median. Why median? Why not mean? And why did we use mean for probabilities? Anybody knows the answer? Online, anybody knows the answer? Why we do median for Sentinel-2 and why do we do mean for probabilities? Yes, outliers, right answer. Who answered? It's catch. So median is much more robust against outliers. Let me give you an example. Let's see, we have some observations. Let's say we have this observations, say reflectance. Let's say we're detecting some pixel. Reflectance of 0.3 in one band, first observation. Second one, 0.25, right? Third observation is cloud, 0.9. Clouds are bright, high reflectance. Fourth observation, 0.3 again. Fifth observation, cloud shadow, 0.1. Again, cloud. So now, if you do a mean, this outliers of 0.9, 0.1 will affect what you're looking at. If you do median, you sort it in the ascending order, the middle value will still be a valid observation. So yeah, so that's the reason. So when we are doing this compositing of Sentinel-2, we have not applied the cloud mask yet. In the composite that I'm showing below, so here, you can see there's still clouds, right? So we have not done any cloud masking for the raw Sentinel-2 images. Yeah, so there we do median. There we do median. And your point is exactly right, that once we master the cloud for dynamic world, we don't have outlier problem. So for dynamic world, we're doing mean. Right? So when you don't have outliers, mean is a better thing. When you have outliers, median is a better observation. So for SAR data, mean works. For weather, climate data, mean works. Earth observation data, median is more robust because we have clouds and cloud shadows. Right? That's the reason we always do median compared to that. Another question, if you ever done cloud masking, you know there is no perfect cloud mask, right? So if you do this cloud mask, you say it has removed most of the clouds, but your pixel still might have clouds. So median is still better there. There is a new data set from Google called what is the what is cloud cloud score, S2 cloud score. Right. So the cloud score algorithm is again a deep learning model for cloud detection. One of the best cloud models I've seen so far. And I've tried, compared all of them, and the cloud score works really good. So if you're search for cloud score, this is launched last month, and it's pretty good. So if you're using cloud score, it removes most of the clouds and cloud shadows. It's really good. In that case, I'll be more confident of using me. But regular Sentinel-2 cloud mask, again, a lot of clouds will escape cloud masking. So median is still better. All right, time for lunch break. After lunch break, we'll continue working on this. So water detection is done. You can use this script, but I want to show you some advanced stuff. So we'll use the kernel operations. If your water body is detected, there's some holes or surround, we'll fill those holes. We'll also remove outliers, have a clean boundary, and we'll convert to vector, download as shape file. So that's coming up after the lunch break. Yes, you can break. Please be sharp. Come back sharp at 2 because we have a lot of material to cover. So I'll start exactly at 2. To the link and you have the presentation. That's all you need for the rest of the workshop. Okay, let's get started. Everybody, anybody new here? Everybody is there. So just a quick recap, what we did in the morning. We are doing the land surface water monitoring example. We started by defining which year and month we need our monitoring for. We took the dynamic world data set, filtered it for images for that particular time period and the region. We computed the average probability of all the bands during that particular period. And finally, we said all the pixels where the water probability is greater than the threshold will be water. And we created our surface water map. So this is the script 1.2 that is linked from the slide. And many of you tried this on your own region. This is a global data set. So you could try this on any region of the world, and you should be able to see the surface water. What I want to show you next is we have this surface water map, and we want to convert it into a polygon of the water boundary. This map is great. It's a good starting point, but we have some problems. So if we convert this into polygon, our polygon would have some holes because there are certain pixels within the water body which are not water, maybe the islands and stuff. And if you convert, you can see this small pixel here. This is a hole here. So there's no water. This is fine. This is doing the correct thing. But maybe if you want to create a polygon, we say, can we just process this a little bit more and fill these holes? Also, you'll see that there are all these small water bodies outside. Maybe our region is just to say, can I get a clean boundary of the reservoir? So I will put a threshold and say anything smaller than a certain area, I will remove. Right? So I'll teach you those post-processing technique. This is also applicable for many other applications that you want to do. So let's learn about the new concepts. So a few minutes of presentation. We have the concept on morphological filters. So kernels is another core remote sensing technique where you are able to change the structure of the image by looking at the image with this neighborhood. And you can apply a function and it'll modify the pixel based on what is surrounding the pixels. And this is how it works. You have a grid of pixels and you say, I want to define my kernel shape and size. So here is a square kernel and the size is 3 pixel by 3 pixel size. And you say, define what are the weights of all the pixels here. And let's say all the weights are 1. And you say the value of the center pixel will be the average of all the 8 pixels. Whatever is the average, I'll replace it with that. So that's a mean kernel. Okay? And once you're done, you go to the next pixel and say, now I'll change that value based on what is surrounding. And this allows you to change pixel based on its neighbors. Right? And it's useful in many contexts where you don't want to process one pixel in an isolated way, but you want to look at what is surrounding it and do that. And you can continue and you can process the image. You can combine a few of these kernels to do something interesting. So what we're going to learn is morphological operations. So the kernel operations can do a lot of things. It can detect edges, it can smoothen the image, it can remove noise. What we are looking at are the morphological filters, which are used to change the structure of the image. Instead of looking at one pixel and say, can I change this pixel? I say, look at the shape of the place and manipulate the shape of that. So how do we do this? There are 2 major operations. One is called an opening operation, where it looks at the structure and opens up any edges where there are isolated pixels. These are the 2 operations. You do a focal min and focal max. Closing operation is where you have holes, you'll fill the holes, and you'll remove any gaps which will close up. So this is for basically dilation followed by erosion. It's also a majority operation where you say, take this 9 pixels grid, replace the center pixel with the majority of what is surrounding it. So if 5 pixels are 1, 3 are 0, and replace by 1. That's a majority filter. It's also called the mode filter. So these are the functions that you see that you can use to apply these particular filters here. So focal mode is essentially a majority operation here. They are called, in your remote sensing software, they might be called, a majority filter or a low pass filter or things like that, right? So this is an Earth Engine implementation of this particular structure of the image. All right, folks who are just joining, we just started this slide on morphological operation. We are using this to remove all the holes in our water detection and remove the isolated pixels that are surrounding. So we'll use that. See if there's a question. Bino has a question online. How is the average calculated in the kernel? I mean, do we calculate for all the 9 bits square within the kernel or leave the center square? So this, you can define the kernel weights and the function. So you can have a kernel weight of 0 at the center, 1 at the beginning. They'll only consider the surrounding pixels. You can have only the cross as 1s and 0. So you can define the weights of each pixel in the kernel, and that do this. So if you want to understand more, pick up a remote sensing book, read the chapter on filters. These are called filters in the traditional remote sensing. So there are very different kind of filters for different purposes. And then you'll know what kernel is suitable for what operations then. Siva online has a very good question. What about the pixel at the corner? So when you apply this, you're sliding that window. What happens to the pixel at the corner? Right? In many implementations, you get 1 pixel less in the output. Right? So if you apply this, you have no value there, you get 0. You get 1 pixel less around 1, so your image will shrink by 1 pixel because you don't do this. So in Earth Engine, there's one line of code which I'll show you, where if you have this image and outside it's all masked, there's no data, you'll get 1 pixel less in output. So what we do is we apply this function called unmask. It means that, have the no data set to 0. So we have the image that is also there, and that means you will not get this. So this corner, you'll get additional 0 pixels around it, and that means you still can process the pixel with whatever the value is there. Since it's a binary image for us, 1 and 0s of water, not water, we can do that. But in otherwise, you'll get 1 pixel less when you apply that. Okay? So make sure masks, again, have a section on masks that will show you exactly how to do this. So if you have an image like this, morphological filters work on binary images. So if you have any image, first make sure you have 1, 0, 1 and 0. They don't work. So you have a water pixel like this. An opening operation will look like this. So if I apply an opening operation, you can see what's happening. Look at this area here in the top. You can see that's why it's called opening operation. If there's a gap with the closing at the end, you just open it up. Also, all this small stuff gets removed, right? So that's the opening operation. Closing operation is the inverse of that. So let's say if you apply the closing operation to this, this is what happens. Look at this whole thing. Got closed, right? It doesn't touch the pixels that doesn't have holes. Right? So for our application, for creating this map of water body, closing is more useful. But we just don't want to touch the boundary. We just say, just fill up all the holes for us. Right? So this is how to do the closing operation. The third one is the majority operation, mode, which will take the majority value within the 9 pixel window and replace the center one with the majority. So this is what happens. You can see it just removes all the salt pepper noise, smooths out everything. Okay. Focal mode is useful where you have this noise in your image and you want to create a homogeneous area of that. Okay. So let's implement this in code from the slide number slide number 32. Take this 1.3 script and open it up. People who are following along, you can take the script, change your geometry to whatever region you want monitoring, delete that, draw a new polygon. First, let's see the code. This is the code for doing the morphological filter. To do a closing operation, we do a focal max followed by focal min. And these are the different parameters. So what is the radius? So radius can be in pixels or meters. So it's a 10-meter pixel of dynamic world. So we said get 3 pixels. So this is my window, 3 pixel by 3 pixel. It's a circular size window. You can do a square kernel, cross kernel with different shapes. We're doing a 30-meter kernel, iterations 2. Do it 2 times. you can also do it multiple times, right? And again, if you are doing some kind of modeling, you say do it once, then in the next iteration is the next year, third iteration is third year, and so on. So you can kind of do this iteration. Here, we just kind of applying smoothing 2 times, and you can do this. Again, this will depend on how much post-processing you need and what you're doing. Remember, doing this changes the pixel values. If you want to get the surface water area, don't do this, right? Because it will change the area of the water. Just say, I want to compute the area of water in this reservoir. Don't do this post-processing because that'll change the area. It's to change the image. We are doing this because we want to create a map, we want to create a boundary of that, right? So make sure whatever detections you get, they are the kind of scientific product. Now we are creating a cartographic product. Let's run this and we'll see what the output looks like. Also note, morphological filters, when you are running this, they take a while to run because they are doing sequentially scanning. They're not like, you can see all of this other stuff, they're processing tile by tile. Each tile is processed by a different machine and you get the result. So it just processes independently. This one can't be done independently, right? It has to do in sequence because it's processing. So you can see sometimes this result takes a while to compute. Let's see the before and after. And try and see the changes in the surface water. So let's see this one. This is a bridge that was part of the road that is going through this. So this was the original image. And when we applied our closing operation, let's see, the holes got filled. So if you just converted the original image to vector, you will get this polygon. But now when you process it and you convert to polygon, you get cleaner polygon. So that's the reason we applied this vector. It's not changing the boundary. It's not processing. It's just filling the holes in the image. Okay, so try it. I'll give you a couple of minutes. Try this on your own region. For folks who are just coming in new, the way if you want to change this to any other region, open a script, delete this geometry, which is at the top. You delete this and you go to any other region in the world. So let's go to Bangalore and we'll go to also Lake. And you can use this polygon tool to draw a polygon. And now when you run it, all of the stuff will happen. You'll find dynamic world images, create a composite, you'll extract the water, you'll post-process and create the results. You can see now we have got the process version of this. This one is the script 1.3. Anybody needs help, please. If you have the results for your own region, please raise your hand. I want to come and see. It's not, you can just sharpen it up. We just need to apply different visualization parameters. So let's take an image. It's easy to better now. Just applying different contrast rate to this. This is just taking the min-max, the distribution values, taking the bottom 2% value, it's 1200 in this region, top 2%, 98% is 2 to 5. These are the pixel values within the range. You can also do a false color composite. So it's false color, you can see it much better, right? So a false color visualization, water is very dark. So if you do water, this might help. Okay, so we are done with this script. Many people have tried on this their own region. That's great. Now, one of the things that people are interested in is we have this binary image, zeros and ones. I want to remove the 0 pixel. I just want to see the blue pixels on the water. All the white pixels I want to remove. Right? Only see the water. Only see the change. Right? So how do I remove the 0 pixels? So that brings us to this problem of masks. So in Earth Engine, no data is defined as mask. And this is a little difficult concept to understand in Earth Engine. So I want to cover that and see how we can apply the mask. It's also important because if we convert this to polygon, you'll get 2 polygons. 1 polygon for the blue part, 1 polygon for the white part. I don't care about the white part, right? I only want the polygon for the blue part. So I want to remove and set all these white pixels to no data. So let's see how to do this. So starting the slides on weight masking. No data values are part of the image which are not observed. So if you have an image that is slanted and you have no observation at the corners, you still need to have a grid of pixels. The pixels at the corner where there's no observation, you set them as no data. Every image comes with a no data value. In Earth Engine, that is called a mask. So if you take any image, there are certain pixels which are not included and will be masked out. So any mask pixel will not be shown. And also if you have 10 values, 10 images, certain pixels are cloud masked. You remove the clouds, set them as no data, and you say, give me the average value, the mask pixel will be excluded for all the computation. As they're just treated as there's no observation. So if you have a mask of the image, I want to update it saying that now I want to change it and say, take my images, wherever there's a cloud, make them no data. Whether there is no water, make them no data. So how do I do this? This is done using this function called update mask. This function takes an image and say image.update mask. You need a mask. So you need to give it another image, which is a binary image. Wherever there is 0 will be removed. Wherever there is 1 will be kept. So take a source image, take a mask image, join it. Wherever there is 1, you retain that pixel value. 0, you remove it. Let's see this in example. Say I have this image. And I have this mask. And I say image.update mask with this mask. The output image will look like this. Wherever there was 1, that pixel was retained. Wherever there was 0, that pixel was left out. So this is how you update your image and say wherever there was clouds, when you do cloud masking, you will basically create an image, binary image saying my metadata says this one pixel is cloudy, this one is not. And you say image.update mask with that mask. Wherever you have zeros, they'll get removed. Sometimes when you're working with this, you'll have to say, I want to do the opposite of that. So you can take this image and call dot not. You'll invert it. So you can do the reverse thing. Sometimes you say, I've detected water, I want to mask out non-water. So you do dot not and replace that. No, it's not multiplication will be just, this is just masking. It's saying you'll overlay wherever the pixels are 0, that part will be removed. Okay, another question. I have an image, I have a mask. What will happen now? What will be the output? This is the image, this is the mask. What will be the result? Huh? what will be the output? Same image? Only ones will be there, right? Yeah. So because here this is the image, this is a mask, all the zeros got removed. But look at the image and the mask. Are they the same or the different? The image and the mask are the same, right? So these two are the same. I just said image, update mask with the same image, and zeros got removed. So now my question is, how do I remove zeros from this image? I have an image with ones and zeros. How do I remove zeros from that image? Update mask with the same image, right? So you say image dot update mask image, and zeros will get removed. This one is very difficult to get conceptually unless you see it. You say image mask with itself, right? So in Earth Engine, there is a function which you might have seen somewhere, image.self-mask. What does self-mask do? It use the image itself as a mask and remove the zeros. You get some Earth Engine code, you'll see self-mask everywhere. This is what it's doing. Whenever you have a binary image, you want to remove the zeros, use the self-mask. Concept is the same. You can use any other image, but since my image is ones and zeros, I want to remove the zeros. I can do self-mask. Let's see the code. Let's see the example. So here is my example. Okay, so you can see I have my inspector is here. If I click here, this is my binary image that I've detected, water, right? Water, not water. So you can say this is 1, water is 1. If I click on this area, so water is 0. Okay, now let me just change this code. I will say when you want to display this, self-mask it. You see, it's transparent. I only see the blue. The white part is gone. If I click on the white part here, it says masked. It's not 0 anymore. It was 0 earlier when we did self-mask, it removed. So now you can see, I can see the base map, base imagery, and I can only see the transparent pixels on top. Super helpful when you're doing some chain detection, right? You only want to say these are the areas. You want to remove all the other parts. So self-mask is used for that. Even when we are doing the conversion to vector, self-mask it before converting to vector. So you only get polygon for this. There's other pixels are gone from the analysis. So let's see the script here, 1.4. So we understood mask. Now what we want to do in the script 1.4 is we want to apply one more step to this. We want to remove the zeros, but we also want to remove small areas. So small cluster of pixels. This is again, when you learn Earth Engine, you're a beginner. This is something that's very difficult to do. It's not obvious how you do this processing. I want to remove all the small patches. I would say anything smaller than 500 square kilometers or 500 square meters. I want to remove. I want to retain only this part. So the way Earth Engine does it, it's using two functions. One is a function called connected pixel count. So here's a code. This is 1.4, where you say, I want to remove anything that is smaller than 10,000 square meters. Each pixel is 10 by 10 meter. So say this is the pixels. So anything that is less than 100 pixels in total, I want to remove. There's a group of pixels, 50 pixels, 2 pixels, those should be removed. So only large water body should be kept. You first take the water image and say connected pixel count. You run this function, it will generate an image where the value of each pixel is the number of pixels it's connected to. So it'll say this pixel, you look at the surrounding and say, oh, it's connected to 1,000 pixels. Next pixel is connected to 99 pixels. right? So each output of this image, this connections, will be the number of pixel connections at each pixel. That's the value. And now you say, select only the pixels where the connections are greater than 100. I want to select all the places where the pixels are connected to 100 more pixels. And that becomes your mask. So you say, I know where are the pixels which are connected to at least 100 pixels elsewhere. And I now take my original image, mask out the pixels which are not there. Okay, so the code here is, it's a water filled dot update mask connections greater than max pixels. So when you do this, connections greater than max pixels, you get a 1, 0 image. One's where the connections are greater than 100. 0 is where connections are less than 100. And when you say use that image as a mask, everywhere there was 0, you get removed. And you can display this. So let's run this. And this threshold is, again, configurable, depending on the water body that you're trying to map. This is my source image. After applying the mask, you can see all these are gone. Nice and clean image of this one. You'll have to adjust this for your own region. If you're trying this on your own region, take the script, adjust how many pixels you want, reconnection. Now we have this clean. And if I just want to show this without any zeros, I will say dot self mask. And self mask is really useful for visualization if you want to visualize the results. So you can say, I want to now say, this is my Sentinel-2 image. I want to know which pixels were got detected as water. So you can see now, I can see the Sentinel-2 image at the behind. It's not zeros, it's not white anymore, right? It's just blue here. This is water, Rest I self-masked it, so it's transparent. You can now compare the image and say, this is where my water was detected. So this is script number 1.4 that we did. So try it out, give you a minute or so. Open script number 1.4, change your region and change the threshold of number of pixels that you want to be removed. And you should see a nice clean version of your data. Some examples of places where I've applied this, worked on a project where they wanted to map forest. They said we would consider a pixel forest if only the minimum patch size is this many hectares. So you do a classification, you detect trees, and then you say, oh, this is too small. I need at least 0.5 hectares for it to be connected with other pixels. So you say, now remove all the small patches. Another for recently, a lot of people are mapping the man-made disasters. So you want to map all the bomb damage through, say Gaza is being bombed. You want to map the damaged buildings. You do the chain detection, you'll get a lot of noise. You'll get maybe few pixels here and there, which was noise. You say I would consider damage of buildings, which is at least 5 pixels together, and that will give me at least some region which is there. So you can remove all the small pixels which are not connected to everything. Right? So applicable, this kind of thing is applicable wide variety where you want to apply or post processing on the image. I want to, in the interest of time, I want to move and show you the last script here. So 1.5, we are done. Remember we started with nothing, right? Very few times you go to a workshop and say, I have nothing, and you'll get a surface water boundary for anywhere in the world. Right? So we started with nothing. We just defined our area, and now what we want is I want the polygon of what the surface water boundary was there. So let's see the script, the last script. This is the complete script that is part of this example. So we want to vectorize it. We first say I'm interested only in the polygons for the ones where the water. So you self-mask it, you get the mask water. And then the function to convert this to vector is something called reduce to vector. You take an image, reduce to vector will take contiguous group of pixels and convert them to polygon. So say, how do I decide which pixels to match? If it's a one band image, you don't need to give a reducer. If you have two bands, the reducer will say, how do I decide which pixels are connected based on these two bands? So this is the default one, doesn't matter. This one is an important parameter, 8 connected. How do I figure out if this pixel is connected to other pixel? Normally, it just take top, bottom, left, and right pixel. If they are connected, they are continuous, and do this. If you say 8 connected true, you'll also look at the cross pixels and say if they are connected, they are also part of that. Many times you want to set this to true, but I've seen that in some cases where if it's true, it generates invalid geometries. You would get this kind of invalid polygons because this 8 connection sometimes can be confused. So my default is always to keep it off and then see if my output doesn't look correct, I'll try the two. And we can run this. So let me run this. It's going to vectorize. So this is the water probability. We have a threshold of probability greater than 5. This is the water that we, with the closing operation, remove the holes. We remove the small detections. And finally, we have the polygons. You can see I have the polygon here. So this is not an image. This is actually a vector polygon. Let's see the image converted into a vector. So we now have a vector polygon that is representing this polygon. And to say this is great, I want to use it in my GIS, so I can create a map or I can do some calculation. You can export it. In Earth Engine, you can export images, you can export vectors. If you want to export vectors, we have this function, export table to drive. When you're exporting the vector, you can define what's the name of the file in the format. So you can export it as shapefiles, GeoJSONs, KML, whatever format you need. You're exporting this as a shapefile, and the name of the file will be surface _water _. And so let's run this. We can run this, and it'll be a task pending for us to run. And when we click run, it'll ask for a confirmation. You really want to start the task. Let's start the task. And once the task is started, you can close Earth Engine. You can close your window, go home, have dinner. Whenever the export finishes, a new shapefile will be added to your drive. Right? There is no export to my computer because some exports can take hours. You don't want to be connected to Earth Engine for those many hours. Just exports to drive, so it's cloud to cloud, and then you can download the data system. There is a question online. You can hear go ahead with the question. You have the, I see a raised hand. If you have a question, you can say now, or you can add in the chat. All right, so everybody can open up the 1.5 script, change your region, and start your export. You can see my export already finished. Okay. I will open up this. You can see it finished. I can open it in Drive and show me the shapefile that is there in my Google Drive. So you can see this one is the shapefile that I just exported. Right? The shapefile consists of multiple files. So all of these files are there. You can download it and use it. There's a question earlier, how can I auto download this? And I have auto download enabled. You can install the Google Drive software. Go to drive.google.com. There's a software that you can install and sync certain folders. So I like all my Earth Engine export to go into this one specific folder called Earth Engine. So I will always export there, and that software that I've installed on my computer, you can see here, this is the Google Drive. The Google Drive folder software, I've said sync my Earth Engine folder. And you can see it's already downloaded. I've not done anything. So let's look at this in QGIS. I'll start QGIS and let's look at the shapefile that we just exported from our page. Doing a lot of export, this will really help. You can just don't have to go and download, it will auto download. Even in QGIS, you can save certain folders as your favorite. You can see my Earth Engine folder is here, so I don't need to go and find it. It's always there. I saved it as a favorite, and I have a shapefile. So this was a shapefile that I've exported from. Yeah. There's a question here on here, right? Yeah. So this function that we use, connect pixel count, takes number of pixels as input. So we are converting this area that we want, say anything less than 10,000 square meters, into pixels. And dynamic world is based on Sentinel-2. Sentinel-2 pixel resolution is 10 meters. So we are saying 10 meter by 10 meter, 1 pixel is 100 square meters. So this 10,000 divided by 100 is the number of pixels that we have. Questions? Anybody having problem with export? For the folks who are thinking this is interesting, I want to now automate the whole process. Every Monday, I want this to be run on all water bodies in my state. I need a shapefile. You can do that. Yeah, you have a Python script. So if you want automation, Python, you have the Python version of the script. You can have a script, set it up on a server that can schedule this every Monday. Set it up so that it's the current date is the end date. Advance minus 1 week is 1 week of that. And it runs it, and you can start the task automatically without it being present. Using Python, you can have a code to start your export task. And I'll set this up for many clients who want to do this, where they say, I want a monitoring solution. So, 100 lines of script, runs it. Don't need to worry about data. Every Monday, you have a shapefile. Right? It runs automatically. So you can implement this. Python is suitable for that. That's why we provided the Python. Moving on. Next one, any questions online? Anything? This is my favorite example of the power of dynamic world. And again, very relevant. It just blows my mind that you can do this with anywhere in the world with this much precision, where you can now monitor urbanization week to week very easily using this. Right? So you can select any region of the world. In this thing, if you are following along, please try this for your own city or for your own house, because you know what changes happening in your region, right? And if the changes that you're trying to detect happen from 2015 to yesterday, you'll be able to detect that. And this is detecting urbanization. So we want to know where is the construction happening, where is the new development happening, and let's see how to do this. So far we've just done detection of water versus non-water, urban versus non-urban. Now what is changing? So it's a different kind of detection. So now we want to monitor change, not just monitor land cover. So we'll define an area, we'll create a before and after composite. We need to define time period. In this example, we are doing yearly change. So we'll say last year, average probability, current year, average probability. And you can compare both. You can set this to monthly, weekly, whichever period you like. But yearly is where you can see most of the changes happening. And how do you find change pixels? You say, give me all pixels which were low probability of urban before and high urban now. That's one way to do this. Or you can say, give me all pixels where there was a large change in urban probability. Something was 0.3 became 0.6. Something was 0.4 became 0.7. Right? So all of those large changes in urban, that's where I would consider urban. depends on what you want to do. Here, what we're going to do is we're going to find all pixels where there is a change in build probability greater than certain threshold over that period. And they'll find all the pixels which are changed. And this time we're going to export this as an image. So you can export this and download this as a geotiff image, overlay in your GIS, and you can say these are all the changed neighborhoods in my region. Let's start the first script. We are on slide 50 using the script 2.1. We are using Bangalore as an example here. So my polygon that I've drawn is over Bangalore. Feel free to change it to any region of the world. And it's amazing what you can see. I was doing a demo where somebody told me, oh, this hall, conference hall that it's a new hall, just got constructed last month. And I changed it to that region. And sure enough, that hall was detected as a change pixel versus a new construction. As you can kind of see everywhere in the world where it's happening. So I would recommend try this for your own region. So delete the geometry, put a new polygon anywhere in the world. We'll do a change between 2022 to 2023. Dynamic world is available from 2015 to yesterday. Okay, so any period between that. Most parts of the world were not systematically imaged before 2016. So ESA, when they launched Sentinel-1, before Sentinel-2B launched, there were not many observations. So if you start 2015, you may not have enough observations. From 2016 onwards, most parts were systematically observed. So you can do changes from 2016 onwards till yesterday. We define our periods. So before start is 1st of Jan 2022. Before end is 1 year from there. After start is 1st Jan 2023. After end is 1 year. We filter dynamic world. And we display the before and after probabilities. Let's just visualize this. We are visualizing only the build probability here. So this is the image. So we are just saying, show me the before and after. So we have this before and after probabilities. Let me just add it on the map without say map.add layer. Go to some region here. So these are the images before and after. You can see there's a lot of changes happening here, right? In this region, you can see there's some stuff happening here. So you can see a lot of changes happening here. Let's see how the probability of urban is changed here. So this is what dynamic world thought of this region. This is just an urban band. So if I inspect here, it says this pixel was 0.7, 70% built before, 70% probably of building up. So it's not much has happened. To see where stuff has changed, here, this pixel. says it was 0.59 built before, 0.68 built after, right? So there's increased probability of being built. So now you have this before and after probabilities of urban pixels that you have, and you can use this to do the change detection. Now you can see there's so many changes happening. Doing this kind of urban change detection is very hard. It'll take a very complex model for you to figure this out. But now, since this has passed through dynamic world knows how you define built area. We can have a simple model which says, show me all pixels where there's more than 0.3 of change. And let's see how that looks like. So let's try the second script, 2.2. So please try this. Open up script 2.2, changes to your city, and find changes. So here's the code for doing the change detection. We have a threshold of 0.3 defined. So we want to find all pixels greater than this threshold. We'll say after image, subtract before image. If the change is greater than this threshold, show me those pixels. Again, configurable, depend on what you want to do. In my experiments with Bangalore and Ahmedabad, 0.3 was giving very good results. So you can, depending on which urban area you want to do, you can try different things. And again, I will self-mask the results and show it on the map. Now I want to spend the time to know how you can interpret these results, because this is unlike any of your remote sensing outputs. So let's go and see some changes. So you can see this is the before region here. This is the after. Do you see the change? So all of these pixels, this pixel here, this is getting built. This one is just roads here. There's no construction here. It's just roads. Dynamic world has detected all of this as changes. You can see this small region also. There's some kind of, people are just kind of started to build, that also got detected as the change. So this one is very difficult to do it in a traditional remote sensing, right? So it's just dirt roads. You just so there's the roads before. Yeah, because this is the CNN network. CNN has a spatial context, and that's why it says it will miss the finer details, because the way its training is done, if you see the training samples that was used to create this model, it says, you see something like this, the whole thing is urban. So if you load the probability layer and you inspect this, there'll be a slight difference of the build probability here and here. You can use it to say, now I want to take all the probabilities, drop points. This is built, this is not built. You can refine those and you can see it. So the detections are there, but the overall, this whole region is considered urban. So this is the only data set which will give you the notion of an urban pixel, not just a built-up pixel. So this is saying this whole region is now urbanized. And again, so this is also the strength of dynamic world and also the weakness. Weakness is if you want to detect roads or this thing, it misses all the final details. But the strength is it can now detect this urbanized regions. Right? So you can now detect urban sprawl. Most time when you're detecting urban sprawl, you're just detecting built-up sprawl. You're not kind of detecting urbanized this thing. So this data set will give you around that. And again, 2 lines of code to do this, and you can now do this kind of change detection easily. And play around with the threshold. That's why I'm saying, your region, you may have to adjust this, and that's the job as an analyst. A dynamic world should never be used without human input. So you are the final decision maker of what you would consider change, what you would consider built up, and that's your input that makes the final product worthwhile for your use case. The last. The last part, we want to export this data. So we'll show you the script 2.3. This time, I'm going to show you one more trick, not very well known. If you export the self-masked image 1, 0, just 1, when you load it into QGIS, ArcGIS, you'll still get those white. Because when you export integer image, which is 0 and 1, it'll be exported as a GeoTIFF integer, 0 to 255. And there's no way to store no data in 0 to 255. So if you want to preserve no data masks in Earth Engine, when you export it, convert it to a floating point image. So you can see that's what's happening here. Where you have this masked image, I want to preserve my mask when I export it to float. And now it will be exported as a floating point image where the no data will be a NaN value, not a number. So probably the biggest question I get, a lot of people, my export still doesn't work, doesn't have masks. You don't convert to float, you will not get masks. Right? So convert to float and we can then export it. So let's see how the export looks like. Run it, it'll ask you for confirmation. Output format, you can see there are 2 formats. GeoTIFF and TF record. There were questions on TF record in the morning. So this is where you can say, I want a TF record. If you want to take this image and do some deep learning, TF records will give you this image patches to do this. But we just want to use in the GIS, so we just export the sensor. And the export will start, and you can see this. I have a script here on this slide. I've linked this script here. If you want to create this animation, I have a script which has a loop. So there's a function which just says 2016 to 2017, 2017 to 2018. Compile this, create a visualization, and export a video. So if you want to learn how to do this, the script is linked here. It's the same concept, but that's in this 1 year change, but we are doing it for multiple years together and exporting that as a video. Any questions while it's exporting? Start your exports for your region. Some of the interesting stuff that when you export something, you can see there'll be this number here. It says the batch compute usage 3309 ECU seconds. This is new stuff. Earth Engine now shows how much computation resources were used to create this image. ECU is Earth Engine compute unit. So it's like if it was running on one machine, it'll take 3000 seconds to do this. So if you are a commercial user, Earth Engine will say, I'll charge you for using one machine for 3000 seconds. And I think the rate is about $5 for 1 ECU hour. So depends on, so if you're doing a lot of exports, you can do this. Even when you're running a script, you have this option here, run with profiler. When you run with profiler, get this tab where it shows you how many seconds it took for each step and how much ECU you consume. Sometimes when you're building a script and saying it's slow, which step is taking more time? You'll get to know, how much memory it's using, how many compute it's using. And if you're a commercial user, suddenly you get $100 bill. You want to know what can I optimize to reduce my usage? You can use this profile. So helpful for debugging. I think this export might take like 8 minutes previously. So it might take more time. I'll show you the results one is done. Another questions on export times. Sometimes once you start using Earth Engine, you get used to seeing stuff in real time. And many times people say, my export took 2 hours. I say, what were you doing? Oh, I was just exporting entire India at 10-meter resolution. So now when you're doing the exporting entire India, obviously there's a lot of computation. If you feel that my computation took long, just look at the ECU second number or ECU hours and say how much total compute you used. So again, be patient with the export. It's also shared resource. When you're running this, there's a pool of machines. You're using that pool. So sometimes people anecdotally will say at night in India, computation is slower because people in the US are all using Earth Engine and doing the exports. So sometimes say yesterday it took 1 hour, today it took 30 minutes. Why? Because there were less users, you could use more resources. Last example for today. So far, we've done 2 things. Continuous monitoring of a land cover class. So we can detect water over time. Continuous change direction. So we can do year-to-year changes and monitor that. By the way, an interesting example, I taught this example a few years back using Sentinel-2, how to declare urban areas. And a couple of years later, some people came to meet me and said, oh, we got inspired by this. Now we have a startup that does real estate consulting based on this. So we are now able to monitor where the construction is happening in Indian cities, and we can now advise people on this. So again, you can now use this data for real world applications on monitoring, construction monitoring. Disaster monitoring, very helpful for rapid mapping. When something happens, I want to map what happened. In this case, we have a specific date of disaster, right? Something happened today or yesterday. I want to know what was before, what is now, and I want to map the change. Right? So slightly different approach. And I want to show you some more tricks that you can use to do this. So here, landslides happen. How can we detect that? So same thing, you take a date, you say, I want image 1 month before to the disaster date to say 15 days, 1 month after, whenever you have the images. How to find change pixels? In this case of landslides, we'll use both of this. So we'll say, I want to know all pixels where the bare probability increased. It was not bare, it increased now. And where the trees probability decreased. So I will use both of those and find out where the changes happen. I also want to show you how to compute area. That's very useful in disaster. Because when you say, first you want to know where is the problem, but what was the total impact? So how much square kilometers or hectares of area got disturbed by landslide. So we'll also learn how to compute area. So we'll start this example, slide number 54. Let's open up the script. Here, you don't change the geometry because landslides didn't happen everywhere in the world, right? So here, you can just play around with the probabilities. This is showing a specific example. And I want to show some of the techniques that will help you work with cloud-free data. One of the biggest problems in disasters is if you have clouds in the before image or clouds in the after image, you cannot compare them. You need cloud-free before and cloud-free after. What happens when there is landslides? What would have caused the landslide? Lot of rain, right? So in leading up to the landslides, you will typically find a lot of clouds because there was a lot of rain and that triggered the landslide. So you look at the image of the landscape before, 15 days, 1 month, 2 months, all cloudy. So how do you manage that? So this is the same case in this particular example as well. This is the landslide that happened in December 2018 in this region, Kodagu region, very severe landslides. So we said this is the date of incident. When you did disaster mapping, this is the date that we work with. Now, if you say I want to know, get all image 1 month before to here, and I want to get the mean probability of trees and bad, well, everything was cloudy for 1 month. But if you know that there was no landslides before, or there were no landslides last year, so what you can do is you can say, I want to get images from up to 2 years in advance, 2 years before, till the date of incident. So give me all images 2 years before to here, but this landscape would go changes, seasonal changes, right? So if I say, give me the tree probability, it includes summer where there might not be trees or might be different thing. So I say, give me images of 2 years in advance, but only for December. So I'm applying 2 filters. The calendar range filter will help you select monthly, weekly, or specific time periods of images. So this will select all December images for up to 2 years in advance. And combining all of those, you will be able to get a cloud image. This works because in this region, there were no landslides 2 years from before. So again, you need to know the region at where it's appropriate to do this kind of thing. But again, calendar range filter is very helpful to get the same time period from previous years also. After, we say, after the date of incident, give me images up to 1 month in advance. This you want to be as short as possible. So you want to say, I want to make it as short as possible. You can also do, say, 10-day, right? If it's cloud-free image, you get all cloud-free pixels, you're good. But you can go up to the time till the landscape recovers. Otherwise, you'll not be able to pick up the changes. Let's run this. And when you're deciding what's your threshold, what bands to use, it's always good to visualize this. So this is the visualization of this area, Sentinel-2 before, Sentinel-2 after. Before probabilities, after probabilities. Right. So you can see dynamic world is picking up the changes, but what is the change? So I can come and say, okay, this region looks like this is a landslide here. I can visually see it. How do I detect those pixels? And use the inspector and inspect this region. So you can see this is the landslide for sure. Okay, I want to detect this pixel. I can inspect this. You can see this is the before probabilities, and these are the after probabilities. So you can see this pixel had the shrub was high, crops were high, trees were high. It's kind of mixed probability, right? Everything is kind of detected as a mixed landscape. Afterwards, so very high probability of bear and very low probability of trees. So you can now figure out what would be your threshold to detect this. So you can inspect around and say, what's a good threshold for this region? And you can find this. Let's see the next script. How do you find the change? I found this threshold just by clicking around. I said, I want the landslides, wherever I want to map those landslides, visually I can see where there's a bad threshold of 0.1 change, trees threshold of 0.2. So there's a change of anything more than 0.2 of changes in forest probabilities and, change of 0.1 in bad probabilities. So here is my bad change after minus before should be greater than this threshold. So it should be more bad than before. So the line that was not bad before, but is bad now, I want to detect those. And here trees, I want before minus after. So there are no trees anymore. There were trees before, no trees now, and I want to detect all those pixels. And either of this is fine. Bare or trees, both are affected by landslides. If you want to detect only the urbanized regions affected by landslides, what would you do? Say, I want to know all the houses that got affected by landslides. How would you, what would you change here? Yeah, so built, you can say bare increased, built decreased, right? So now you can kind of decide on the model of what you want to detect. You see stuff in red. These are all the pixels that matched our condition, where there was a big change in bare and big decrease in the tree probability. You can export, convert to polygons, export this, and say, now I know everywhere the landslides happen. And you can zoom out the region. You can just say, zoom out to entire district or entire state and map this. Area. How many people have computed area in Earth Engine? Anybody has done area calculation in Earth Engine? In other software, area calculation is just a button, right? You have this image, give me the area. In Earth Engine, it's not so simple. Because Earth Engine says, oh, you may ask me to compute area of water bodies in the entire world, right? So I can't just, go and find all the pixels and do this. So Earth Engine has to implement it in a way that can be computed in parallel. So let's see how to do the area. The first two ways of calculating the area. First, we want to know the area of a polygon. So I have a geometry, I've drawn a polygon. How big is this polygon? That is simple. If you have a geometry or polygon, you can call dot area, will give you the area. Area in Earth Engine will always be in square meters. Whatever projection you're using, doesn't matter, always will be in square meters. So when you compute geometry.area, you'll get square meters. So these are the square meters of this polygon. This function also takes a particular projection. So you can specify a particular CRS and say, I want this area in UTM or area in this particular projection, and you compute using that. If you don't specify it, Earth Engine will use spherical calculation and compute the area of that. If you are implementing something in Earth Engine and you say, I computed area in ArcGIS, it says 16.12, for example. Do others, Earth Engine 16.09. Who's right? Well, they're using different methods. If you want your results to match in the software, you specify projection. Reproject your data in ArcGIS or QGIS to UTM, specify your same projection here, you'll get the same area exactly. For raster area, what we want to do is we now want to compute the area of each pixel. So what is the total area affected by landslides? So what is the area of all the red pixels in this region? Okay. We detected we have ones and zeros. I want to know, sum up all this area and do this. The way Earth Engine does it is first it wants to know, it'll compute the area of each pixel. So I have different pixels, compute area of individual pixels, and then sum it up. Why individual area? Because depends on the projection, this pixel and this pixel in a different area. Right? Latitude area differs by latitude. Or if you are doing in, on a sphere, as you go up, the area changes of the same size. So again, you can specify a projection, it'll reproject your image into that, compute the area of that. And But if you don't specify this, you use this function called image pixel area. So this is a function which will compute the area of each pixel. And you multiply it with this image. So I have a change image, ones and zeros. What happens when I multiply ones and zeros with this area? Wherever there is 1, that pixel's value will become the area. 0 will be 0. So now I have this ones and zeros, I multiply it by this function. Now the pixel values are the area of that pixel. And I can sum it up. In Earth Engine, summing is done by this function called reduce region. So give me the sum of all the pixels in this region at 10-meter resolution. You run this, you get answer in square meters. This is the total area of square meters in this pixel. You divide it by 1,000 times 1,000, you convert to square kilometers. And now when we run this, you'll say this total area was 16 square kilometers, and the red pixels, the one that we detected as landslides, was 1.29 square kilometers. Questions on area calculation? Yeah, so when you are doing this calculation, this function reduce region, many functions in Earth Engine, export functions, calculation functions, they will say just to ensure that you are not unnecessarily exporting something very large or not taking a very large computation, it puts a limit. The default is that 1 million pixels is the limit. So if your region has more than 1 million pixels, it'll stop. Say, oh, you are trying to export an image that is about more than 1 million pixels, or you're trying to do this computation which has more than 1 million pixels. This is just to prevent new users to accidentally doing something very large. Because in nothing you can say my AOI is whole world, export, and suddenly you say my drive is full, right? So to prevent that, it's configurable. So once you know what you're doing, you can change this. So I always specify max pixels to be 1 followed by 10 zeros. Right? So it's like very large number you can do this. And you might think 1 million is large enough, but if you take Sentinel-2 image of Bangalore, 12 bands, or say maybe a Bangalore district, 12 bands, 1 million pixels would be easy. Right? So all this is configurable. You can specify this. Just to is there to prevent new users from extending this. Yeah. So in export functions, you will always have a scale parameter. So let's say in the previous example, we did the whole thing, right? And when we're exporting this, export function will always ask you for a scale, right? So, and the way Earth Engine works is when you run your script, it runs backwards. So Earth Engine says, user is asking me to create this image. User wants to see the result at 10-meter resolution. You can specify projection also. So user wants 10-meter pixels in UTM for this region. What do I need to do this? So I need dynamic world, I need Sentinel-2. You'll reproject all the original images to that resolution and that projection, and then do the computation. So the computation will run on the output scale and projection specified. When you're loading these images on this canvas here, this canvas is in EPSG-3857, Web Mercator. So when you're running this, it's implicitly reprojecting all the source images to Web Mercator and showing the results. When you export it, you can specify whatever projection is. So the question is, yes, you can run this, you specify 100 here. It will start your analysis by resampling dynamic world to 100 meters and then do all the computation. So, all the parameters, that's why even in the area calculation, you have the option, your scale. This is computing, taking the whole analysis is done at that resolution, and then you compute the area. If you want something quick, sometimes they say, I want to compute the area of all the water bodies in India. But that might take 10 minutes to do it. So I just want an estimate fast. Say, do it at 1 kilometer resolution. You'll get an estimate because it's resampling everything at low resolution and just doing it very fast. But using native resolution will give you the most accurate answer. So you always use that. But for sometimes quick visualization, you can do this. Okay, I think we are coming to the close of this. Want to quickly show you the Colab notebooks for people who want to do this in Python. The Python package that you want to use is called EE. In Colab, it's already installed. So you can just import EE. This is a pain point in Python that every time you run your notebook, you have to run authentication. So you have to run this authentication. It'll give you a link to go sign in, approve, you get a code, you put it. This has to be done every time you start a new Colab session. Because Colab is run on a virtual machine that gets destroyed after a few minutes. So again, every time you run this, you have to authenticate. If you're doing this on your own machine, if you have a Jupyter notebook locally, you don't have to do this. You just do once, the token is saved, and you can do this. We are using this GMap library. This library gives you this map canvas and all the tools that are not there in the core API. This also comes pre-installed now with the Colab, and you can use this. Let me just show you the process of doing this, because many people are, maybe if you're not familiar with Python, there's a slightly different workflow to set up your environment and do this, but the result will be the same. You get the same output, but in a slightly different way. So first step, you connect. You'll be connected to a Google Cloud machine. You can see it's connected to a machine having 100 GB of storage, 12 GB of RAM, and again, Colab provides you free of cost. So this is a machine that you bought. You can pay for Colab Pro. It will give you better machines. So import E. Second step, E authenticate. Don't check this box. This says you only have read-only access. That means you cannot export data to your account. So very common thing. People see this box and they are read-only. Click, and then my exports are failing because you don't give access. And you get this token, copy this, enter. And you can see saved token. And now when you run initialize, everything will work. Define your region, it's the same thing. This is your map, and this is your image. And same thing, you can see the code is identical, there's no change. You can see all of this is the same code. Though this Python, API is the same. So everything is same. Few syntax difference. If you want to continue the line, you have a backslash in Python. In JavaScript, you don't need it. So there's no semicolon. All of this small differences, but otherwise, this is the same. Then you find the change pixels. So you found all the change pixels here. This is the urban example. Do this. And finally, this is the new stuff you get in Python, where you can have an export task. And without clicking any button, you can say task.start and export will start. So this is what will help you automate your process. You have take this whole code, put in a Python script, it'll run on a machine without you being present. So you can just say task.start and just export and finish that. So that's the Python version. We have Python notebooks for all three examples. You can use that. Quiz 2, ready? Okay. Everybody get ready? You know the drill. I'm going to open it up. It's closed now. I'm going to open up the quiz. Yes, open. Start. Quiz 2 is on slide number 55. Speed and accuracy both. Somebody's first, but not accurate. So take your time, do this. We got a first person to get 10 on 10. One more. One more minute and I'll close the quiz. Please submit. Ten seconds. Right, I'm going to close this. Come on, submit if you're not done it. Quickly. Okay, let's see the answers. If you have a binary image with pixel values of 1 and 0, how can you remove zeros? All the correct options. Which are the correct options? Image.update mask image and self mask. Both of these are correct, right? So the self mask is doing this thing. You want to map deforestation caused by agriculture, what would you do? You want change in trees and change in crops, right? So both together. So you want to do this together. Which function can help you remove salt, pepper, noise, and smooth image? Local mode. Majority, right? Mode is the majority of it. Want to monitor changes in a mangrove forest, what would you do? Right? One is, if it's a coastal region, you can use the flooded vegetation. Most of the flooded vegetation around the coastal region will be mangrove, so you can use that band to do this. Or if you want to be more accurate, reclassify dynamic world using local training data. You can do a classification, say mangroves, water, mangroves, and now you have more accurate mangrove model, which you can use to do change detection. And the article that I linked shows the process for that. And also it links to a video where I taught a dynamic world workshop in Nairobi, Kenya, where we had people actually come in, refine dynamic world using the real ground truth data. And they got really good results of mapping forest and crops and all of that. Right? So you can see those results and some more examples of refining dynamic world using local training data. Pixel area is a function for raster. Dot area is for vector. Both of these are useful. Sunil Kumar, great job. Congratulations. Shiva, Shiva is online, right? Yes. So congratulations,
Yes, sir.
Shiva.
Yes.
One more
Thank you,
prize.
sir.
I'm going to ship you two things. I have a mouse
Yeah.
pad
Thank you,
and
sir.
a mouse. So I'm going to ship you. Congratulations. Good job.
Thank you, sir. Thank you.
We have Anjali. Yes. You got mug already, right? Or mouse pad? Okay, you can take the mouse pad. You're going to be your your lab will be full of Earth engine stuff. As I mentioned, I'm not going to go with any of the stuff back, so I'm still going to give away some more prizes. So let's go down the list. Super. That's it. And finally, Santosh, you can come up here. Thank you for your help and support. So, get one. All right, so we come to the end of the workshop. Few concluding remarks, and then we'll end it. I'm here in the conference for next 2 days, so feel free to grab me. Happy to talk with you, show you scripts, show you code, and we can discuss this. But I want your feedback on this workshop, right? So first, spend 2 minutes, do this feedback. So everybody go. And this is an anonymous feedback, slide number 56. This takes 2 minutes. You're not collecting your names or emails, so I don't know who it is. So you can give honest feedback. You say this was complete waste of time. It's fine. That's useful feedback for me as well. So please give honest feedback. Stuff you liked, stuff you didn't like. So you know what you want to do with this. That is really helpful. So let's do 2 minutes of feedback. Folks online as well, please do the feedback. It'll be really important to me how this model works. Usually I'm teaching people online and people are watching offline. This is the first time teaching offline and people are watching online. So I want to know how this went and you know what we could have done better to make your experience better. And if you thought something didn't work, please mention that. So I would love to. So please do the feedback. The form is linked from the same slide deck. And even if you're around, you can just share the direct link to the form as well. Sure. Lastly, if you didn't use Earth Engine, or even if you use Earth Engine, if you want to learn more, I have lots of free resources. I'm spending all my time creating open learning resources. So whatever level you are, complete beginner, intermediate user, advanced user, you'll find materials here. This is the link. You can go and use this. I'm just going to show you what resources are there, and everything is free and open. So open also means that you can take it, teach a workshop using this, or if you want, you can create a startup using this, whatever. It's open source, whatever you want to do, you can do this. Free means, again, you don't need to pay for this. I have this workshop. If you've never done Earth Engine before, do this. This is a video recording of a recent workshop. You can just watch the videos and do this. There's a book called EFA Open Access Book. So this was a recent book project. 100 authors, experts in Earth Engine came together and we worked on this book project. It's open access. It's also available as a PDF or online version. And it's got chapters on both fundamentals of Earth Engine. So EFA stands for Earth Engine Fundamentals and Applications. So you have how to do stuff in Earth Engine, how to apply a mask, how to do convert to vector, how to do map reduce, all of that. But also it's got chapters on applications. How do you apply Earth Engine for agriculture? How do you apply for built environment? How do you do air pollution monitoring? And all of these are written by experts who have worked on this along with videos. Each chapter has a recording of the author teaching the chapter. And the video is available, right? So if you prefer learning over videos, all the videos are also freely available. You can just watch that and you'll be able to learn that. So really, this shows there's a lot of effort that went on this. So I wrote a few chapters. So if you want to start from the first one, this is my chapter, and you can kind of go sequentially and back that. So really useful resource. And again, we have a lot of courses, videos, projects, go through this list, whichever level you want to do. Working on a new course, advanced concepts of existing earthen users, stay tuned for that. Is partly done, reducers, regressions, data fusion, all of those both will be available. So with that, I want to end the class. Thank you all for your attention.